So what is tening? Tening. Y'all didn't pick that up? What we do, the problem we have, first of all, is with different types of things, especially like the soldering iron. The soldering iron itself, it's not machined, so it's got a surface. If we was to magnify the tip of the iron, it would look something like this. And then the surface that we're soldering to is not perfect, so it's going to do this. So the problem is we're only trying to transfer heat where the metals meet. So what we need to do is have something that fills that gap. So what we do is we tin the iron. So tinning is a process of pre-coating something with solder. And then what happens is you got this solder on your iron already melted. And then when you solder, it comes in and does what? Fills the gap, and now you get maximum heat transfer between your iron and whatever you're soldering. And then he used the term wetting. What's wetting? He threw it out a couple times. What we're trying to do when we solder or braze or anything that we deal with welds and stuff like that is we're trying to get the metals hot enough to melt the solder. And what happens is the molecules of the solder bonds with the molecules of what we're trying to solder together. And this process of bonding is what we refer to as wetting. So wetting is when the molecules of the solder actually bonds with the metals that we're soldering together. And what we're shooting for on these leads, and you looked at his, is this thing that looks kind of like this. And why we're doing that is that if we can see where it actually merges with the pieces of metal, we know we have wetting. Does that make sense? And if we come over here and see it like dip in like that, then we know we don't have wetting, so that means something wasn't quite right. Either we didn't get the oxidation off the surface of what we're welding together. Anybody knows when you weld, you have flux, right? Y'all weld before. When that flux, that's what it's in there for. It's trying to get that oxidation off the surface before, so the weld actually bonds with the metals, right? You understand that? So brazing, so what we do, first of all, is we need to get rid of the oxidation. So what we use, so wetting, that's the bonding of the surface molecules, of the molecules of the solder with the surface molecules of what we're trying to solder together. And then flux. What is flux? Well, it's a cleaner is what it is. Now, you got to be real careful because we have two fluxes that we use in soldering. We have what we call acid core flux, and then we have what we call rosin core. And what we mean by core is you saw we put that little old picture up there. So actually in the center of the solder, this is where the actual flux is located. Now, you can buy flux also for soldering, but we use what we call rosin core solder. Rosin core becomes highly corrosive when it's hot, but when it cools down, it becomes inert, and it's a good insulator. So what we use, and make sure when we use, when we're soldering electronics, we use what we call rosin core solder. And this doesn't say anything. So flux, this is just what we use, and even in welding, you use flux also if you do that. Brazing. If you do brazing, then you use acid core because you're dealing with copper pipes and stuff like that. When you're dealing with electronics, but the problem with acid core is it always stays active and it'll cause problems on electronics. And plus, acid is a conductor too. So acid's a pretty good conductor, right? You understand? So what we use is we use rosin core, what we call rosin core solder. Are we okay so far? Yes or no? So first of all, when we pick the iron up, we make sure, when we put it away, we make sure it's tin. And then when we pick it up, one of the first things we do is tin the iron. And we'll show you all that in a minute. Are we okay? Now what we use is, we use a ratio of, so what ratio of solder do y'all use? Do y'all use lead-free solder? Or do y'all use, so what's an alloy? Two or more. So you gotta have two or more, right? You gotta have two or more, at least two or more. So solder is an alloy. And the main alloy that we use in electronics is what we use tin and we use lead. Tin lead alloy. Let me find the PowerPoint. I need to get it over here. Let me pause this. So we'll look at what we call tin solder, solder, and what they call silver solder. And then, there's the quiz is up here. Oops. So solder terms: alloy, solder, eutectic, tin, lead, silver ratio, welding, flux, tinning, and slag. What's slag? It's impurities that rise to the surface when you melt metals. Right. So we got to deal with slag, right, when we melt it. So this is a solder alloy. And what's really neat is that the different ratios, and this goes through several different ratios of lead and tin. So tin has tin melts at about 450 degrees. Lead melts around 621 degrees. And this is centigrade, guys. And then we start ratios. So a ratio of 10 parts lead and 90% tin. This would be solid anywhere between 450 degrees. And then between 500 and about 776, it would be what we call in the plastic state. If you ever worked in a steel mill, this is where they roll the steel. So the steel, when they shape it into form, they have it in the plastic state. So it's not a liquid and it's not a solid. Now what happens is we keep going through these ratios and we hit this ratio right here, 63:37. The melting temperature is 361 degrees centigrade, which is around 700 degrees Fahrenheit. And notice what happens. It has no what? It has no plastic state. This is called eutectic solder. So when you get up to 361 degrees centigrade, this sucker 1 degree above that, it would turn into a liquid. And when you drop below that, 1 degree below that, it would turn into a solid. And this is called eutectic solder. For some reason, that is not the most popular solder. The most popular solder is 60-40. 60% lead and 40% tin. Now lead, guys, is cancer causer, right? You understand that. But lead, the molecules of lead are not big. They're too big to be absorbed through your hand. So handling solder is not the problem. The problem is taking your hands and handling solder and then doing what? Licking on your fingers or stuff like that, right? There's a lot of houses that still got lead paint out there, and when it starts chipping, that's the problem. Is kids go out and do they eat it, yeah. So lead is, but if you got any cuts on your hands or anything like that, then you need to make sure that you put on some type of gloves or something when you solder, right? You understand that? And also, when you get through soldering, what's the first thing you should do? Wash your hands. Go to the restroom, wash your hands. Don't use this sanitizer. All you do is make the lead sanitary, right? You understand? And move the lead around. So make sure when we get through soldering every night, then everybody go to the restroom and wash their hands a little bit. Are we okay? So this is the flux. It's actually in the center. Like I said, we use rosin core flux. These are different types of soldering irons and soldering guns. We use soldering guns. These guys are really, they do fast soldering jobs, but we do these for really pretty good sized jobs. So y'all use an iron or y'all use a gun, dummy? And then we have different tips. Basically, the variations between the tips depends on what you're doing. I prefer this semi chisel tip, and you can get these different sizes. So what you want to do is you want to make sure you get a tip that covers what you want to solder, right? Everybody okay? Now the technique is you pick it up and you do what? It's already on. So what's the first thing you do when you need to pick up the soldering iron? Huh? Clean it? Clean it? Huh?
It said that before you put it up, put salt on it.
No, first thing you do when you pick it up, you clean it with your sponge, number one. Because what that's going to do is that's going to get any of the slag or stuff that's on there. Because right now this thing has been sitting here. And let me bring up my camera.
It said you're supposed to put salt on it.
Yeah, before you store it too. So when I look at this, you see how awful it looks? And that's slag, guys. I'm going to come up here and just take this and wipe it on my sponge. And now all of a sudden you see that nice tip there, right? Can you see it? And look how fast it turns. So it's already turning. So the first thing we do is we pick it up. We come up here and clean it. And then what do we do next? Then we re-tin it, right? Yeah, we re-tin it, right? Are we okay? And of course, before you store it, you want to coat it with some iron. You never want to file these things to get because the problem is copper, and copper flux eats copper up. I mean, and so what happens is transfer and heat pretty much, the best transfer of heat pretty much follows the best conductors of electricity. So soldering tips are usually made out of copper. Well, if that flux gets on that copper, what's it going to do with the tip? It's going to eat it up, right? That's what it does, and it stays hot all the time. The flux stays active. So what they do is they coat this with a really thin coating of iron. These are called ironclad tips, but it's really, really thin. And what's that on there? It reduces the efficiency of the iron just a hair, but what it does, it doesn't. It's not susceptible to being eat up by the flux. And if you come up here and file that off, and you file off that cladding, and then your tip's going to eat up, right? You understand? So about the only thing you should clean this in. Steel wool works real good to clean it if you got oxidation on it. Another thing you got to be ready is that when you get a new iron, and you plug it in, you need to sit there with that solder and tin that thing the first time. Because if it comes up and gets that oxidation on there, it's really, really hard to get off. So if you ever get a new iron, you need to do that. Also, these guys right here, this is what he's talking about. I usually only use this when I really, really want to clean the tip of my iron. Okay, if y'all can see that, if I don't touch my camera. Okay. The first thing we do is we pick up the iron. First thing we do every time is do what? Clean it. And even while you're using it, every once in a while, you're gonna clean it. If you see it getting slag in there, you're gonna come up and re-tin it. Then what he says you do. What you need to do is put your iron and make sure it touches all the metals you're trying to solder together. The soldering iron basically is not doing the soldering. The metals that you're soldered together is doing the soldering. And if you've ever done any brazing or anything like that, you understand that. You get the metals up hot enough and then you touch the solder to it. So what we'll do is we'll come up here, we'll tin it, we'll put it down. Normally what we do is we touch this solder on this side between the lead or what we're trying to solder together just to get a good solder joint there. And then we always end up soldering on the opposite side. If you can't solder on the opposite side, it means you either got oxidation on it and your flux didn't get it off, or you just don't have both surfaces up hot enough to melt the metal. We okay? That makes sense? Everybody okay? Yes or no? So what we're looking for this volcano effect. So we don't want to cover things with solder. If you got a big old blob of solder on there, I cannot tell if we had wetting. If we don't have wetting, we don't have a good joint. So what we got to do is we see where it comes in on these joints, and we actually see where it merges with what we're trying to solder together. When we pre-tin wires, so it's very, very popular. The big advantage of solid strand wire over stranded wire, it's easier to terminate. We can come up and splice. I mean, if you ever did any house wiring, how do you splice house wiring? I know what splicing means, right? What's splicing? Two conductors together. How do we splice most solid strand wires in your house? Well, first of all, you better twist them together. If you ever see an electrician, just stick them up there and twist that thing on there. You need to fire them. You're supposed to twist it together, and then you put the wire nut on there. So, and then when we terminate it, you just usually wrap it around a screw and screw it down. Stranded wire. What's the advantage of stranded conductors? Nobody knows what the advantage of stranded conductors are. These are stranded conductors. Yeah, stranded conductors are a lot more flexible. The problem is that the wires try to do what we call bird cage. When you try to screw them under something, they try to spread out. And if you lose one strand, you've changed the gauge of the wire, right? You understand? If you use a lot of them, then you got a problem. So usually when we termination is the act. Every conductor eventually comes to an end, right? You understand that? The function of the current, the function of the conductor is to get that current from the power source to the load. And that's the function of the conductor. So we terminate it at the power source and we terminate it at the load. So that the act of bringing the conductor to the end that's what it's referred to. So normally when we terminate solid strand wire, we either put it in some type of compression joint so if it does board cage, none of them gets out, or we put a terminal on there. We put a ring terminal or a slide terminal or some type of terminal on there. In crimping, usually we either solder, splice stranded wire, or we come in and we use what we call butt splices, which is you just crimp them on there. So the advantage of solid strand over solid is that it's easier to terminate and easier to terminate and easier to splice. The advantage of stranded is that it's a lot more flexible, but it's harder to terminate and it's harder to splice, right? We got to use special stuff to terminate that stuff. Anybody that's ever dealt with just regular house wire, and we're dealing with 14 gauge wire, and it's solid strand wire, and that stuff is very hard to move and to manipulate. You know, you get up into those 8 gauges and those 10 gauges that you run over to your HVAC system or stuff like that, and it's really, really hard to handle that solid strand wire. But what do you do when you terminate it in a wall outlet? You just wrap it around a screw, right, and screw it down. So what we do a lot of times on the wires, instead of on the stranded wire, what we do is we'll tin it, we'll coat it with solder, and in that way, just the very tip, and then it acts like a solid strand wire, and then we can do a lot of the things we can do. But when you tin the wire, you're supposed, and I'll show you how to do that too, even though I don't think there's some tinned wires in the kit you're going to put together, but these have been pre-tinned by the people that actually put the kit together. So tinning is what? Yeah, coating something with solder. So we pre-tin solder some stranded wires. We'll pre-tin those. Uh, a lot of times before we splice them in different types of splices that we do. So what we do is what we're looking for on these components is I'm looking for this what?
Okay.
Now this volcano shape. And if you cover up the tips and you can't see it or if it bubbles. So what happens if you put too much solder on it? So normally when we get a cold solder joint, let me find a place where I can. So a lot of times you'll see this, where this is the eye. By the way, we call this a solder eye. This is where the components solder to. And our components, the labs that we're putting together, these are what we call single-sided boards. So what we do is we only solder it on the back side. So we'll have a solder eye on the bottom and the circuit card is up here. So when we put our components through it, we're going to put them through this side like this, and then we'll have the components sticking up. Usually it's going to bend over. I'll show you why. Right? And then what do? We bring our solder and iron wire, and we make sure we're touching both of them, right? You understand that? And then what do? Just touch a little piece of solder there to get the solder to flow, and then you're going to do what? Move your iron to the other side, make sure you're touching both sides, and then you'll end up soldering on the opposite side. I always end up soldering on the opposite side.
When you go to transition to the other side, is the solder on that wall?
No, solder only has a plastic state of almost no time at all. So what you're going to notice is almost as soon as you get that iron off there, that solder is going to turn into a solid. Okay. And then solder is really neat in that you can heat it and reheat it, and it always works, right? You understand? Once you've got wetting, you can always take it off. So we can use a solder vac to do what? Take it off and resolder it. If we got too much solder on there, it'll wick toward heat. So a lot of times you can clean, if you got too much solder on there, you can just clean your iron off really good and stick it back down there, and it'll actually wick off onto your iron. If you got a lot too much solder, then what you probably need to do is to use a solder vac and take it off and then resolder it. But no, what happens is, and we don't want to move, we don't want the components to move, because if it moves when it's going through that plastic state, then you'll end up with a cold joint too. So this is why we're going to come in here when we load these things. We're going to bring them through like he showed them, and then we're going to bend the leads so that way the components won't fall out, right? You understand? And then we'll clip them and then we'll solder. Are we okay? Are we okay? So we're using 6040 rosin core solder. I like a really, really thin diameter, because that way you can control the flow of the solder a lot better. So this is the solder. And this is a 0.8 diameter. And it says alloy number 60. I don't know about that. 500 grams. But this is the solder I like to use. And this we'll give out. We have bigger gauge solders that you would use if you were going to do more soldering, because it would just take so much of this. You'll go through this thing real fast. Are we okay? So, like he was saying, so if I was going to do some soldering, so this is not what y'all going to put together. Y'all going to put together a lot simpler kit than this. This is one of our robots. So what you're going to try to do when you do your solder, number one, is you're going to try to make it look like a machine put it together. So what you're going to find out is that all your resistors that are mounted horizontal, you want them all to turn the same direction. So you know we're using what we call 4-band resistors. So it goes color, multiplier, tolerance, right? All these are gold tolerance, which means they've got what? What's gold? 5%, yeah. So these plus minus 5%. Anything above this Anything below these, so go would be the biggest one you see on these 4-band resistors, I mean the smallest tolerance. After that, we move to 5-band resistors. And 5-band resistors, it goes number, 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 multiplier. And then you'll see like a brown. And what do you think a brown would be for a tolerance?
2%.
So brown is brown is 1 on the chart, so it's 1%. And then, so red would be 2%. Then they jump real crazy, guys. Like purple is like 0.5%. So even though it's got a 4. So there's a lot of other things that we run into. What we're going to do, of course, is you have the 2 holes right here, right? And we're going to come up here and we're going to gauge this. And then what we do is we use, what we try to do is center the component. And then we can use needle nose pliers to gauge where it goes, right? And then when you bend it, you always want to bend it between the actual component and the actual where you're going to solder it to. A lot of people are grabbing things and bend it like that, and that's not good because these guys are just mechanically connected to the ceramic in there, and you can very easily pull it out. And plus what it does with that bridge right here, it gives the component the ability to expand and retract with heat. If you snug that thing down and it heats up, it could actually pull the leads right out of it. So you want that little space in there. And then what do you say, dude? So you're going to insert it right. Check your color code, because one of the things you're going to be graded on, of course, is that all your vertical resistors need to be pointed in the same direction, either tolerance up or tolerance down, right? You understand that. And then we're going to come up here, and what did he say, dude? Go ahead. Not yet. What you do is you want to bring it through. You don't clip them first. You bring them through, and then once you get them through, this is where you bend them right here. So you bend them on this side. So now the component is not going to fall out, right? You understand? So what can we do now? We can come up and clip it probably around 1/8 of an inch. I usually say the width of my fingernails. And by the way, you need to make sure you hold on to these things when you clip them, because what'll happen is they'll fly out, right? So we're going to make sure we got safety glasses on when y'all do this. Once it's loaded, I'm going to pass this around. This soldering job right here is pretty good. Another thing you want to do is you want to make sure the eye is covered, right? So I'll pass this around. Let me find it again. Right here. So this could be, so this is not if it focuses in. So what happened is when they soldered it, they just soldered one side and it didn't go all the way around the eye. So what's happening is it's only being supported on one side instead of being supported all the way around. No, I want to see holes. In fact, I wish we had a double-sided board so I could show you how to do that. But this guy right here, most of it, so there's one right there, he didn't get enough solder on. This right here, yeah, it did get enough solder on, so that's not a good joint. This one right here is totally awful. You can see where they left the solder on there too long, let it get too hot. I got some of the leads way too long. The problem with cutting your leads too long is this is the perfect example right here. Is the person didn't, if this can focus in, the person left the lead too long, and now when the thing is set down like this, what happened now? The 2 leads touch together. So that's why you don't want to go much past the eye. So this is a very poor example. This right here is not really great. But this guy, the problem he had is he left a lot of them only soldered on one side. So now if you got a lot of vibration, you've only got one support on one side, right? You understand? So this is my, so this is from previous labs that we did. And I call this the good, the bad, and the ugly. So these are just some of the terminals or different methods that we solve. Now when you solder conductors, this insulation has to be, listen, this insulation has to be within 2 wire diameters of what you're soldering to. It's like how much exposed, the more exposed wire you have, the more likelihood it's going to short against something, right? And this right here should be flush. Can you see where the problem had problems? So he's left way too much overhang here, and he did what? This is not within what? 2 wire diameters. Now this is just awful, really bad and really ugly. Look how much space he left between his splice there. That's not too good, is it? This same thing. The joint itself looks good, but whoever did this did not get this within. So your wire, the insulation should come all the way down to right about here. This guy didn't do a good job. Looks like when he stripped it, he nicked the wire really bad, so he's got a bad spot here, and then he melted, got his soldering iron up against the thing. And you can't see when you're doing wires, you want to actually still see the strands of the wire. You want to still see the wetting, right? You understand that? I don't know what this guy did. For one reason, the wire is supposed to go in here, and this is what we call bird cage. You see the way the strands are really just spread out there? So what this person didn't do, he didn't twist them together really well before he soldered them. This guy looks real good. That's a pretty good looking joint. So notice within 2 wire diameters, I can still see the strands of the wire, right? That's good. This is a good job. Within 2 wire diameters, I can still see the strands of the wire. This is a printed circuit board, so this is awful. So you see what this person did. The person got the thing too hot. So they start off with a fiberglass board, then they coat it with copper, and then they etch it. They expose it to light, and then they etch off everything that's supposed to be etched off. So this copper is just glued on there. And what happens when you get glue real hot? Yeah. Most glues let go, right? You understand? And this is what happens here. This guy right here lost actually three eyes. I mean, 3 eyes. I'm sorry. Solder pads or solder irons. This guy. So look, he got this is impurities in there, which means he probably didn't clean his iron off. Too much solder, it's bubbling out instead of bubbling in. He's got his leads cut too long, right? You understand, which means they could do what? Short out if the board was laid on. Now this guy. Everything, yeah. Too much solder, leads clipped too long, excessive heat. So what happened is he left the heat on there so long it burned the eyes up, and he actually got the slag on the circuit card. We don't know about these. Why don't I know about these? Because he's covered up the eyes and he's covered up the lead, and we can't see the what? Can't see the wetting, right? So we don't know. If I can't tell a joint is good, I assume it's bad. This one, he got what we call a solder bridge. Can y'all see that? Which is really bad. This is a surface mount, by the way. These did not allow the solder to flow too. So when you have a double-sided board, you're supposed to leave it on the solder enough so it actually flows through to the other side. So you want it soldered on both sides. But he did get his components in there right. This is good. Cause y'all see, can y'all see the thing? See how this one, every one of these look really good. We okay? This bottom left one, this is the one that's built, this is the one that's bent over. So this is, he didn't bend this side over here. It looks like he only bent one side. And what usually happens when you only bend one side, a lot of times either the IC will come out on that side just a little bit. It's hard to solve.
Is there not hard to solve on the bend over on both sides?
Well, all we're going to do is bend it on this side and bend it on that side, and it's not hard. It's
So I
not.
don't want to bend the back, so it's solid on the back side of that. You put the wire around.
Well, when you're right-handed or left-handed, so I would put my iron up against here. So what you're going to do is you're going to touch right here on both metals, and you just come over here and touch the solder on the side over here.
The little heat, you got track through that, so you don't have to touch the beginning.
So notice here they got all their watt tolerances turned in the same direction. They got their. If you want to work on a board, get on one where when they rotate the components, they don't put it so you can read the values up. So you notice he's got these guys, all of them's pointed so we can read the values up. So this is a really good job. Resistors, the same question. Components oriented correctly. Component values can be read. Solder was allowed to flow through. You can see that they actually soldered on this side, even though the person only soldered on the other side. This is a good job. This is a good job. I can't see this, but this is a good job too. Now y'all not dealing with a double-sided board, so you don't have to let it go through like they do on a double-sided board. So now, used to, we had a component side and then we had a solder side. So you had one side that your components mounted on, then you had the side that you actually soldered on. These components right here have become known as through-the-hole components. So they actually go all the way through the circuit board. More and more we're running into, what we're trying to do is we're trying to make the solder, another reason why we bend the leads a little bit is to get some mechanical support. So we would like the component to give us a good mechanical support and then the solder to give us electrical support. But what's happening now is we're getting ICs that's got so many dang pins on them that they actually do what we call surface mount. I'll try to find some surface mount devices where the ICs actually mount on the surface. But these guys are going to have a bunch of pins, or either they're going to be really, really small. So now they're mounting components on both sides. So we'll see circuit cards now, especially memory. If you got any memory on your computer, they'll have memory integrated circuits on both sides of these things. So it's getting away from this. You'll still run into this a lot. So y'all ready?
10 minutes.
10-minute break?
Yeah, then we'll be ready.
All right, then we'll go over there and let y'all pick y'all up.